Thank you. I apologize for not speaking Finnish. I would have maybe managed to read my presentation, but I prefer to speak live. So I'll put it there. Yeah. So as Yrjö said, my presentation is quite a lot related to his presentation. So here we are dealing with those indirect emissions as well as those direct emissions. We combine them together. I have quite an extensive list of co-authors. I put on the list all the people who have been involved in the project. Some of them don't work anymore in the institutions, but they are there they are mentioned. Everybody did own share. The background of our work was that around 1/3 of energy in Helsinki, I don't know if that is true still, is produced from hard coal, and Helsinki wants to become eventually carbon neutral by 2050, and before that reduce carbon emissions quite significantly. And the idea was, could coal and wood pellets co-combustion be part of the solution? We in Syke, we are experts in life cycle assessment. So life cycle assessment was applied, and we tried to figure out if the desirable or desired reductions could be achieved. This was the studied system, so Salmisaari power plant of Helen, and the aim of the study and the methods were follows. So we want to perform life cycle assessment, LCA, of the operational phase of an existing power plant for different scenarios. Operational phase means that we didn't look at the physical infrastructure of the power plant, but only on the operation, fuel supply, and direct emissions. The functional unit was defined as annual operation of the power plant, 6,500 hours, producing estimated 1 terawatt-hour of electricity and 2 terawatt-hours of heat. This case was partly based on the real data, but of course was adjusted. This is a model. This is not a real case scenario. The data came from Helen, from the environmental impact assessment reports, from scientific literature, from suppliers of fuels, and from various LCI databases. The impact assessment in this study was performed according to recipe midpoint impact category, impact assessment, and the following 5 impact categories were selected as relevant for this case. So it was climate change, fossil depletion, terrestrial acidification, photochemical oxygen formation, and particle matter formation. For particle matter formation, we had a subtask in our work to look at the wood pellets supplied by trucks and apply the Finnish regional emission scenario to figure out whether transport of pellets would make a significant difference to fine particle emissions within the city. So what did we study? We compared the existing coal system with 2 prospective co-combustion systems. We had a power plant, we had Salmisaari producing heat, electricity, and coal, and the base case scenario was 100% coal combustion. So that's basically situation until like a year ago. So 100% of fuel is supplied from hard coal. And then the first prospective scenario was 7 pellets co-combustion scenario, where 7% of fuel, of energy in fuel, would be supplied through wood pellets, domestic wood pellets. And then the second prospective scenario was defined as 40% pellets co-combustion, where minority of those pellets would be domestic, and then most would be imported from Latvia and from Russia. So these are the 3 scenarios. On the left side, you see that's the upstream or those indirect processes which contribute to the indirect emissions, and on the right side there are those direct impacts or slash emissions. And now we can move to results. These are normalized results which represent relative contribution to the impact categories. So normalized, we could have them in one figure. What we can see is that when implementing wood pellets co-combustion, we could achieve a reduction in climate change impact category and fossil depletion impact category, while there could be observed slight increase in acidification, photochemical oxidation formation, particulate matter formation. The increase is not very big, it's a couple of %, and as I said, this is a model, so it's hard to say what the reality would look like, but based on our model, this is the case. So if climate change impacts are in the focus, and if we follow the LCA methodology, then co-combustion of wood pellets would make sense. This is just a picture of the fine particle modeling of our colleagues here in Syke. That figure represents the route of truck transport when domestic wood pellets would be transported to the power plant, and I don't have to maybe explain the figure because there would need to be one more figure, but so the conclusion of this work was that in the 7% scenario, the impact of truck transport would be absolutely minimum. It wouldn't really make any difference on the fine particles emissions in the city of Helsinki. It wasn't applied. This model wasn't applied on the 40% scenario. Just to put into perspective these results of climate change impact category, greenhouse gas emissions of Helsinki metropolitan area in 2011 were about 6 million tons of CO2 equivalent, and this 40% co-combustion scenario could yield to about 500,000 tons of CO2 equivalent reduction. So that's pretty significant. Here's a closer look at pellets production. As I have mentioned, some pellets would be domestically sourced, some would be imported, for example, from Latvia or Russia, or there might be also other options. And you can see that the environmental profile of pellets produced in different countries actually differ quite a lot. And for example, the Russian pellets, they are not made of sawdust, which is a byproduct from sawmills, but it is these are made from round wood. So forest is cut and then chopped, and pellets are made. So that's one difference. The other difference is the type of energy which is used for drying sawdust in the wood pellets production. In case of Russia, that's the yellow part of the bar. Natural gas is used, and quite a lot of it. In the Finnish case, that's the brown part of the bar. That's peat consumption, burning of peat in order to dry sawdust. So that's you can see that that type of heat which is used in pellets production really matters. Here I have one slide on which is a discussion on climate impacts of biomass combustion. These are the results of the 40% scenario and the 100% coal combustion. So we see a significant drop in CO2 or in climate impacts. However, there are still CO2 emissions emitted from the chimney naturally. We are combusting a fuel. We are combusting, in this case, wood pellets and coal. And if we characterize the CO2 emissions, biogenic CO2 emissions, in the same way as we would do for coal, then since we need more pellets in order to get the same amount of energy, compared to coal, the emissions would even increase. But that's not the case, because we know that those are biogenic emissions which have been sequestered in forests and will be sequestered again. But we cannot currently, with the current methodology which we have available, we cannot say how much smaller the blue section of the bar would be, but certainly much smaller than what. This is just an illustrative picture telling that there are still biogenic CO2 emissions emitted to the atmosphere. A few take-home messages. Life cycle assessment helps to avoid problem shifting. We are looking at several different impact categories at the same time, and we can see what the impacts of our decisions what kind of impacts can be observed based on the decision we make, and we can try to optimize the system so that the environmental impacts would be decreased equally. The origin of wood pellets and their feedstock matter. That was the figure where I showed you Finnish, Latvian, and Russian pellets. Feedstock, is it round wood or is it sawdust as a byproduct, so basically waste? And another take-home message concerning wood pellets production is that it's important, or it's essential, to ensure sustainability of pellets production in order to gain the environmental benefits. So it's not only the energy in drying and pelletizing, but maybe even more importantly, the forestry practices and how carbon flows and stocks and albedo effect and other very complicated issues which I can't myself fully understand how those are handled and modeled. And the effects on the power plant's operation will be fully understood then when this larger scale co-combustion will be implemented. We didn't obviously have data on direct emissions of the higher share co-combustion, so only future will tell. Thank you.